G, there's this special subgroup, which is called the Commutator subgroup. It's denoted G prime traditionally, rather uninformingly. G prime. So what that is, so look at its angle bracket. So it's a subgroup generated by a set of elements. The set of elements are these special products. These are called commutators. AB, A inverse B. These are the kinds of things that we expect to be the identity element if the group is abelian. So if the group is abelian, it means you can reverse A and B always, and the whole thing cancels down to the identity element. If the group G were abelian, these are the things that should be the identity. So if the group is not abelian, then this subgroup is of interest. You gather together all the things that should be the identity, and you look at the subgroup generated by them. Then the factor group, well, first of all, this will be a normal subgroup of G. So you can do the factor group. The factor group is abelian. Yeah? And if any factor group, if any G mod H is abelian, that can only arise if H contains the commutator. So the commutator is the smallest subgroup that you have to factor out by in order to get an abelian quotient group, an abelian factor group. So it's the minimal amount of stuff that you must quotient out by to get an abelian group. And if any other quotient is abelian, it must be at least quotienting or factoring out by the commutator subgroup. Okay. So we proved the different elements of that yesterday. Okay. So what we're going to see now is example 15.14, which will be an application of that. So the claim now is that if the group G has order a particular product of primes, so 1, 6, 4, 5. It's quite a big group. So if that factorizes as 5 by 7 by 47.
What page is it on?
246.
246, yeah. Well, it's saying there is really only one such group. So it's one of these strong classification results. A group of this size, we're going to show that G has to be isomorphic to Z1645. Cyclic group. Cyclic group. So essentially, there's only one group of order 1645. So proof of this. Well, it's proved with a combination of thinking about this concept of the commutator subgroup and also with the application of Silov's theorem. Sure. First of all, we consider the Silov 47 subgroups. So there is a subgroup of size 47. This 47 divides the size of G. So how many of these? Well, how many, let's say K, is the count of these. K must be congruent to 1 modulo 47, and K must divide, well, the size of G, but really it must divide the other factors, 5 by 4, 5 by 7. So K must divide 35. So which numbers that are congruent to 1 mod 47 divide 35? Well, only one. Okay. The other option, 48, is already too big to divide 35. This remember is coming from the third Silov theorems. Third Silov theorem. So the number of Silov subgroups divides the prime that is congruent to 1 mod prime and divides the size of the group. So this implies K equals 1. So only one such group, only one such subgroup of order 47. call it H1. Now, there's only one of these, it's normal, okay? Because every conjugate of H1 is a subgroup of size 47, but there's only one subgroup. Every conjugate of it must be it. That's the standard argument. There's only one subgroup of a certain size, that implies H1 is normal. So we can speak of a factor group. This exists, and you can do the factor group. And the size of it, well, when you factor a group, it's easy to say what the size of it. It's the size of G divided by the size of H. So it's of size 35. Now this is an example of theorem 15.10. Yeah.
Why couldn't it be 35? Why couldn't it be a subgroup of order 35 rather than 47?
Because we're focused. So 47 is one of the primes dividing G.
Okay.
So by C, so we're focusing on the prime 47.
Oh, it has to be prime.
To speak of a C log P subgroup, yeah, the P has to be prime.
Okay.
Yeah.
So that's why we can choose 35.
We're not, yeah. So does G have a subgroup of size 35? Well, it'll turn out that it does. But that's not what the C log subgroup, C log theorems speak about.
Because that's not P.
Because it's not a prime. Yeah, yeah. You just look at one of the primes dividing the size of G, and then the C log theorems tell you about subgroups of, they tell you about P subgroups.
But couldn't it be 7 or 5?
Oh yeah, it could.
Why didn't you choose?
Well, this is, well, we just choose to look at the largest one because this is going to make the argument. This is going to make the argument work. I think you could also make it work by choosing any other one. I think. Well, let's follow this through first, and then we'll see, did we have to start with the prime 47? That's a good question. Well, anyway, so theorem 15.10, you see 35 is the product of two primes. And the larger one is not congruent to 1 modulo the smaller one. See, theorem 15.10 spoke about groups of this kind, whose order was a product of two primes, where the top one was not congruent to 1 modulo the smaller one.
Which theorem did you say?
15.10. And the conclusion was that G was cyclic. Cyclic, and so it's isomorphic to Z35. And also, hence abelian. Because cyclic groups are abelian. Cyclic groups are abelian, right? So that implies, if you go back to our commutator, that implies that our commutator is contained in or equal to H1. Now, what does that say about the size of what does that say about the size of G1? H1 is size 47, which is a single prime number. So that means the order of G prime is either equal to 1 or 47. Okay?
Can I just ask
Yeah,
a question?
that's great. Yeah.
Why did you say, so we said it's cyclic because it's not congruent to 1 mod 5? Is that why it's
So cyclic by an application of theorem 15.10. Theorem 15.10 gives you the conclusion that the group is cyclic, and the group has order the product of two distinct prime numbers, where the bigger one is not congruent to one modulo the smaller one.
Okay.
Which is again proved using the C-log theorems.
So it's cyclic.
Yeah. And there's only one, so all cyclic groups of size 35 are isomorphic to Z35. They all look the same. They all look the same group structure. Well, if okay. We can also apply this. So now we know the size of the commutator is 1/47. So now this speaks to Mario's point, asking me, why did we start with 47? Well, maybe there's no reason to start there. We'll start with it. Can also apply this reasoning to the primes p equals 5 and 7. And exactly the same conclusions go through. There's only one subgroup of each size. Let's say this H2, which is size 5, and H3, which is size 7. There's only one C-log 5 subgroup and only one C-log 7 group. For the same similar reasons. And again, so there's only one that's normal, so you can speak of the factor group. Both factor groups, when you look at them, are abelian. So that's going to imply that our commutator subgroup is contained in H2, and our commutator subgroup is contained in H3. But contained in H2 is size 5, so that means the size of the commutator subgroup is 1 or 5, and the size of the commutator subgroup is 1 or 7. So for whatever one you look at. So how can this be resolved? How can all these conditions and the size of the commutator subgroup be resolved? Here we've said it's 1 or 47. Here we've said it's 1 or 5. Here we've said it's 1 or 7. So what must it be? Well, 1. It can only be 1. So it's a subgroup of size 1. So we know exactly what it is. It's just the identity. Right? It's just the identity. So again, it's just the identity. So that implies for every A and B and G, when you look at any of these commutators, A, B, A inverse, B inverse, it's always the identity. These are the elements that generate the commutator. And that's equivalent to saying AB is BA. Commutator being the identity is the same as AB is in BA. Multiply both sides on the right by B, multiply both sides on the right by A.
I've got a question.
Yeah.
So why if it's 1 or 5, why did you choose 1 between them?
One is so it's the same G prime we're talking about.
Yeah.
So how can it have size 1 or, I mean, we only need 2 of these conditions. It's size 1 or size 47, size 1 or 5. Well, already we know it has to have size 1.
Why?
Because it's, so it's like saying you are 1 or 47. And then someone else comes along and says you are 1 or 5. So then you know you are 1.
Oh, okay. Because 1 is common between them.
1 is the only thing, yes, the only way they can both be true.
Okay.
Yeah. And if you add on the third one, it just reinforces that. Yeah.
And why did you say there is only one subgroup of order 5 or 7?
Well, I didn't go through all the steps, but that's by applying the Seelov's third theorem. These conditions on the number of these subgroups. So how many 5 subgroups are there? It has to be congruent to 1 mod 5, and it will have to divide 7 times 47. The only way that can happen is if it is 1. Yeah. You look at everything congruent to 1 mod 5, and that has to divide 7 times 47. It has to be 1 mod 5. It has to be 1. And similarly when you look at H. So i.e. here, what we're saying now, we're saying very strong conclusion, G is abelian. G is abelian. And so by fundamental theorem of finite abelian groups, the FTFAG, remember that a few chapters ago? It must break down into direct product cyclic groups coming out of the prime factors of G. But when you look at it, it's going to be have to be Z5 cross Z7 cross Z47. And these are all pairwise, these are all distinct primes, they're all pairwise co-prime, so it's actually just isomorphic to Z mod 1645. The product of all these. So it's another case of an order for a group where there's a very strong classification result. There's only one group of that size. Now these are few and far between. You know, your typical order of a group, you expect many groups of that order. Okay, there's a lot of possibilities. But for certain types, we can limit the number of possibilities. The next two examples, 1515 and 1516, are fairly straightforward. Just application of the Selov third theorem. Just applying these conditions, you know, that the number of Selov P subgroups is congruent to 1 mod P and divides the size of the group, and just drawing immediate consequences from those. A new, slightly new technique arises in 1570. Which is a counting argument or an enumeration argument.
I'm going to count the lowest level of confidence with it and upstream. Which is
Because your project's all about
So the statement here is, if G has order 56, we expect multiple groups of size 56. If G is order 56, then G is not simple. I.e., it has at least one normal subgroup. Remember, simple group, well, a person in the street could tell you a simple group is one that can't be simplified. But we understand that to mean that there's no normal subgroups, no proper non-trivial normal subgroups. No, sorry, it has at least one genuine normal subgroup. Proper non-trivial. Trivial subgroup is always normal, the whole group is always normal. So every group has a simplified version, which is the group itself. That's the factoring out by the trivial subgroup. Or if you factor out by the whole group, you get trivial. But there you've rubbed out everything. So it's quite spiritual. So what we're arguing here is that G has an interesting normal subgroup. Genuine, intermediate, mid-sized normal subgroup. And so you can factor out by that and get a simplified view of G. So G is not simple. So the proof comes by applying the Selov theorems, but with some careful enumeration as well. So the size of G is 56, which as you all know is 8 by 7. So it's 2 cubed by 7. So let's focus on the largest let's focus on the largest one and ask ourselves how many seven subgroups. Okay. So let's say this number is k. So this number k has to be congruent to 1 modulo 7, and k has to divide g, or divide the size of g, so it's divide 56, but really, because it's congruent to 1 mod 7, it's co-prime to 1 mod 7, so it must divide 8. So what conclusions do you draw about k in this case? What could k be? It must divide 8, so there's not that many choices. And it must simultaneously be congruent to 1 mod 7. 8 would satisfy those two conditions, and 1. 2, 4, no. 2 and 4 are not congruent to 1 mod 7. So k is 1 or 8. Right? If k equals 1, then we're saying there's only one subgroup of size 7. Usual story, therefore it must be normal. Because every conjugate of a subgroup is a subgroup of the same size. So if there's only one subgroup of size 7, every conjugate of this subgroup is itself. And that's a condition for normality. The conjugate of every subgroup H is its H itself. H is 1. So if k equals 1, by the usual reasoning, this subgroup is 1. So H, subgroup of size 7, is normal in G. It's a proper non-trivial subgroup. It's got size 7, so it's a proper intermediate size. And so G is not simple.
So if in exam we just say normal reasoning, is it acceptable? But usual reasoning, is it acceptable or not?
It depends what the question is. If the question was this, then yeah, because this is at a higher level beyond, here you're talking about something about the definition of normality. If the question was, prove that if there's only one subgroup of a certain size, it's normal, but then you could just say, well, by the usual reasoning, that's true, because it's asking you directly to prove that. But if it's like this kind of question, which is at a further point, then yeah, I mean, if we're in the middle of an argument here, we probably won't stop to prove, if something is obviously a subgroup, we probably won't stop to prove all the details of it because we're at a kind of higher level in this discussion. So, that's the kind of. But if you're in an exam, I think you maybe would. I mean, here I'm just saying because we've referenced it a few times in today's class and this class, so that's why I'm kind of using that kind of phrasing. Okay, so this applies generally. If there's only one subgroup of a particular size, it is normal. Yeah, that's a good thing to remember. Okay, but this is if k equals 1. K does not have to be 1. What if k is 8? Remember, the goal here is to prove G is not simple. So k is equal to 1, we get our goal. What if k equals 8? Well, then we have 8 subgroups. If you want, you could label them H1 to H8, each of size 7. They're all different. Because there's 8. I mean, it doesn't need to be said. They're distinct subgroups. But each of size 7, what do their intersections look like?
Identity.
And the identity only. So each HI intersect a HJ. It only ever consists of the identity element. Why is that true? Well, you see 7 is a prime. If there was a non-trivial element here in the intersection, if there was an X here, X would be in HI, it would also be in HJ, but X would have to have order 7. So it's a non-identity element in a subgroup of size 7. 7 is a prime. Every non-identity element has to have order 7. So if X is order 7 and it's in HI, that means HI is generated by X. But it's also in HJ, so HJ would be generated by X. So HI would equal HJ. But I mean that two different ones here. Yeah. So if you take any two of these groups, they only intersect in the identity. So here's where the counting argument comes in. Remember, there's a limited number of elements in G. There's only 56 elements in G. So these subgroups count for how many elements?
Okay.
Yeah. Don't you do it wrong.
No.
If we consider this collection of subgroups, how many elements do they take up? Well, there's the identity element, which is common to all of them, right? So then each one has 6 other elements. Yeah? But they're all distinct. Yeah? The 6 elements, 6 non-identity elements in H1, they don't appear in any of the other ones, because all these intersections are trivial.
Yeah, but I just don't understand why did you say there isn't, you said but I didn't get it right. Why there isn't anything else but the intersection between them?
Okay, so we need a little proof of this. So proof of this. Suppose X was an element of HI intersect HJ, and X was not the identity. Then the order of X is 7. The order of an element has to divide the order of the group. These groups both have size 7. So the order of the cyclic subgroup generated by X is 7. But cyclic subgroup generated by X is contained in HI and contained in HJ. But HI and HJ have size 7. So if they contain a subgroup of size 7, they must be equal to that. So that implies the cyclic subgroup generated by X is equal to HI and equal to HJ. So that implies that HI is actually equal to HJ. So if you take two different ones, they can't be equal. So the intersection must only be trivial. Can you see that?
Yeah.
Yeah.
Thank you.
So now that we know that they all have trivial pairwise intersections, how many elements are accounted for? Well, there's the identity element, and then in each of them, there's a new batch of 6 elements. Each is size 7, the identity and 6 non-identity elements. And there's 8 of them, so you've got 8 times 6 non-identity elements, which is 48, plus this element, 49. Okay, we've accounted for most of the 56 elements there. We still don't know G is not simple, so now we look at the other prime too. How many C-log 2 subgroups? So this number K must be congruent to 1 mod 2, and K must divide 7. Yeah. So that implies K is either 1 or 7. Now we're talking about C-log 2 subgroups. These subgroups have each of size 8.
I'm just wondering, when you write 1 plus 8 plus 6.
No, 1 plus 8 times 6.
Yeah, why is that?
So I'm counting up how many elements we see here.
Okay, 6.
There's 6. In each of these, there is the identity element.
Okay.
There's
And
each
6
subgroup
other
And
elements.
6 other elements.
All right, okay.
There's 8 of them.
Yeah.
And this little proof here proves that the 6 non-identity elements in each one are completely distinct from all the others.
Mhm.
So it's a different 6 each time. So that's why we got 49 elements. But you see, the CLOV, these CLOV2 subgroups of size 8, subgroup or groups of order 8. So how many more of them can we fit in? See, we've only got 7 elements left to find. The group is size 56. And we've already accounted for 49 elements. None of these 49, well, apart from the identity, none of the 48 non-identity elements here can be in the CLOV2 subgroup. Because these elements all come from CLOV7 subgroups. They all have order 7. The elements of order 7. So they can't live inside a group of size 8. The order of an element must divide the size of the group. Well, there's only 7 elements left to account for. So there's only room for one CLOV 8 subgroup, CLOV2 subgroup, which has order 8. It's order 8 because it's 2 cubed, appears in the size of cube. So this is our normal. This then, under this case, where there was 8 subgroups of size 7, therefore, there would only be one subgroup of size 8. So it would be normal, so G would not be so. This would imply this is normal. The subgroup of size 8 is normal in G, so that implies G is not so. So it's a kind of 2-case conclusion. Because up here we have the original count of the CLOV7 subgroups was 1 or 7. If there was 1, G, then that CLOV7 subgroup is normal, so G is not simple. But if it was 8, that's taking up so much room that there's only room for one CLOV2 subgroup. It would be normal, and therefore G is not simple. Okay? So that's what we mean by a counting argument, an argument that relies on enumerating the elements and drawing conclusions from that. Any questions?
Yeah. When you say there is only 7 elements left to account for, and then you say so only room for one CLOV2 subgroup. Why only one?
Well,
room for one.
These 49 elements are the identity and a batch of 8 times 6 elements, but they all have order 7. Okay? So they can't be elements of this subgroup of size 8. Because in a subgroup of size 8, every element must have order a factor of 8. So you can't have elements of order 7 in there. So the only elements available to populate this subgroup of size 8 are the ones you haven't counted here. So there's only 7 more left to go up to 56. So it's those 7 elements plus the identity that make up the 8 elements of this. So it's so constrained that there's only one subgroup of size 8. Because you've only got 7 non-identity elements left over. You can only form one subgroup of size 8 from those 7 elements.
Why only one?
Well, because you have to take those 7 and the identity. And there's no other elements around to make a subgroup. So it's a quite, in a way, I know it's difficult to work through when you're seeing it, but in a sense, it's quite basic reasons, because it's just simply lining up the elements and counting them and seeing what's available. Yep. Okay. We did make use of this lemma in an example last week, but I must admit, one of the tutorial exercises we did that last week, we did it before we were kind of ready for it. We should have seen this example 1519 done first. But that relies on 1518. So he's saying, for other kinds of groups, it's not so simple to prove they're not simple. It's more difficult to prove that they're not simple. Again, he's taking another specific example, groups of size 48. Now down here, he proves that a group of size 48 is not simple. It must have a proper intermediate normal simple. So it's a similar kind of conclusion that we've seen in the previous example. But he's relying on this lemma here. Now, I don't think we've got time to do both of them. But I'd like to do this one, especially since we need a correction here. It's got a mismatch here. So, yeah, I think we can do it without writing it out, I think. So this lemma is about judging the size of a product of two subgroups. So it's quite general. H and K are any two subgroups of a finite group G. So the product of the two subgroups, well, this is all we know that is, in general, this is only a subset. Under certain special circumstances, it's a subgroup. In general, it's a subset. It's a subset formed from every product, every possible product you can form, taking an element from H and an element from K. Now, you might be tempted to think that all these products you can form are distinct. That's not necessarily the case. Okay? So this lemma is about controlling, or is about examining how big this subset is. So it turns out it's given by this quite simple formula. So it's the size of H times the size of K. That's the number of ordered pairs HK you can take. Yeah, something from H and something from K. The number of those such pairings is the size of H times the size of K. But as I've said, there's the potential that a number of different pairs could multiply together to give you the same element. Well, the way we account for that is we divide out by the size of the intersection. So here's how the argument goes. So this is the product H times K subsets. Certainly its size is less than or equal to the product of the two sizes. Okay? Because maybe every possible selection of a pair of elements gives you a new distinct element. In that case, the size of H times K would be equal to the size of H times the size of K. But it's potentially small. Since some element in HK could be written as the product of different elements in HK. So this is what we're talking about here. Suppose a H1 K1 was equal to a H2 K2. So by implication, two different pairs, H1 K1, H2 K2, that nevertheless multiply together to the same element. So if this is the case, then, well, you just reorganize this equation, multiply both sides on, what does it do? Multiplies both sides on the left by H1 inverse, and multiply both sides on the right by K2 inverse. So then you get this equation. Yeah? This equals this. So let's call that element A. Now, when you look at the first product, you see that A is an element of H. Yeah. Look at the second product. A is also an element of K. H and K are subgroups, remember? So H1 inverse is in H, K2 inverse is in K. H and K are close. So what we're looking at now is an element A that belongs in the intersection. Okay.
But if you multiply the left-hand side by H1 inverse, it has to cancel H1 anyway.
Yeah, it
They
does.
don't cancel each other, why did you just write H1 inverse H2?
No, so let's multiply both sides on the left by H1 inverse. It'll say K1 is H1 inverse H2 K2. And then you multiply both sides on the right by K2 inverse. So you get K1 K2 inverse equals H1 inverse H2.
Yeah.
Yeah, you agree?
Yeah.
So those two are equal, so we call this element A.
Okay.
Yeah. Now here's the bit where we have to correct it. He's gone wrong here. So certainly A is in the intersection, but now H2 is not H1A inverse. H2 is H1A. So this is H1A. Multiply H1 on the right by A, using this form of A, you get H2. And this is A1 inverse K1. A inverse K1. Okay. He's just got a bit mixed up there.
Does that carry through?
No, it's
At the
correct.
end of that.
It's correct from here on in. Yeah. So what he's saying here is, if there's a second pair that multiplies together to give you the same value as another pair multiplied together, that second pair can be generated from the first pair by multiplying on an appropriate side by an element from the intersection. Yeah. So that's in a way an explanation for how this second pair came about. They're generated from the first pair by choosing an element from the intersection and generating H2 and K2 like that. Conversely, he's going in the opposite direction. He says if you take an element from the intersection, yeah, generate a second pair, it's called the unadorned H and K. So H is generated from H1 and this element B. No, actually, sorry, we should make the appropriate correction here as well. So the H is generated by, well, it doesn't matter. It just comes down to whether you call this A or whether you call this A inverse. I mean, they're both elements of the intersection. So I think it's neither here nor there. But here he says if you take an element from the intersection, generate the second pair H and K from H1 and K1, according to this rule, then when you multiply H by K, you see the B inverse cancels with the B. If you multiply H by K, you get H1K. So what this is saying is here's a connection. Whenever you've got two distinct pairs that multiply together to get the same value, the second pair is related to the first via an element of the intersection. Okay. Conversely, if you take an element from the intersection and generate a second pair H and K from a first pair H1, K1, you get a new pair that multiplies together to give the same element. So this is like a one-to-one correspondence between elements of the intersection and different pairs H and K that give the same element as H1 times K1. So this is how he gets his conclusion here. Any element H times K from the product of the subsets can be written in a different form as many times as there are elements in H intersection K. As we just set up a kind of one-to-one correspondence. there is any other way of representing the product, it comes via this rule from an element of the intersection. And conversely, if you apply this rule to any element from the intersection, you get another pair that multiplies together to give the same value as the original.
So is that like basically like if the intersection is only the identity, there's only one way to write each pair?
Yes. There's only each pair, each distinct pair gives you a distinct element
Yeah,
when you multiply the elements together.
but the bigger, yeah, that makes
The
sense.
bigger the intersection is, the more different pairs there are that multiply together to get the same element. So that means, what's the size of the product of the subsets? And how many distinct elements are there here? Well, it's the total number of pairs, but divided out by this kind of multiple counting effect. For every element of the intersection, there is a new distinct pair that multiplies together to get the same element. So the total number of distinct elements must be this quotient here. So that gets that proof here. And then now with this lemma, we can tackle these groups of size 48. Unfortunately, not today. But maybe on Thursday, we could go over that argument again, because we kind of did it. We did a second version of it for another order in a somewhat haphazard way. Jan kind of went back through here and realized that it was another example of the application of this method. But unfortunately, I wasn't expecting it to use this result. So we can re-examine this. We can look at this example on Thursday and start to pick up a few more exercises as well. Well, I think from this point is as far as we're going to go with new fresh material. Okay. So we'll do a few more exercises from chapter 15 when I see you on Thursday. Then I think we'll begin looking back over the whole thing. So I think I might make some suggestions for things we might look at in next week's lecture. We'll do a mixture of looking at past exams and picking appropriate problems and groups out of the book. Okay? Okay? And I'll produce the exam solutions and the guidance things we've talked about as well. Okay? Good.
No, just send out the emails on graduations.